All right, I think we're going to start. Hello and welcome to the first edition of our Generative AI or Generative Vision and AI Meetup series. We are so excited to have you. I know we all miss these physical meetups and the free food, but I'm so glad that we're adjusting to the new normal, and this is great. So thanks for joining. We have a lot today, so let's get started. First of all, this meetup is being hosted by and it's being co-hosted by NVIDIA, so thank you so much for that. We would like to request everyone to stay muted during the entirety of the meetup. If you have any questions, there will be a Slido link that will be sent out over the chat in a few minutes. Or at the very end after the talks, what we're going to do is we'll probably open it up for questions and then we'll take it one at a time. Okay. I think before we jump into the series, I would love to talk about a little bit about our company. As you know, Brighter.ai is a data privacy startup. We started in 2017. We mainly came out of the autonomous industry, automotive industry. And it's really interesting because we worked with NVIDIA a lot, and then we even won an award called the hottest startup award in Europe. So that was pretty cool. Since then, we've grown to about 20 people. We're based right here in Berlin. We closed our funding round last year, and we're looking to grow. So we're definitely hiring. If you think there's a fit, please reach out to us. All right. So next up, I want to give you a little idea of the meetup. I'm not sure how many of you already know what this series is about. We've done a few meetups in the past. So essentially, when we started out, what we wanted to do was build a community around generative vision, right? We wanted to get people together. We wanted to have these brilliant minds talking, debating, arguing over tabs versus spaces, have a little fun watching them debate that. But this year we realized that, these generative vision things, they don't lie in a vacuum. They're related to so many different things. There's a business side to it. You build a prototype and suddenly you are thinking about scaling it or talking about development. And so we thought, okay, how about we expand our horizon a little bit, right? And we not only talk about generative vision, but also these different aspects. And so that's really where this came in. Today, if you look at our topic, we're talking about scaling in AI. And so we'll get into that aspect and how we have sort of a story and a narrative prepared for you, so you know exactly what the speakers are and why we're approaching this topic. So before we go into speakers and before we do all of that, I want to do a quick shout out about the pizza situation. As you remember, I talked about free food. I miss it too, but we're trying to do the best we can. And so if you remember in the meetup description, we have this thing where we're going to have a raffle and 10 lucky participants will get pizzas. And I'm happy to announce that there are people who have already gotten their pizzas. People who sent us their full addresses have received it. If anyone still did give us their full address and didn't receive a pizza, please shout out to us. If you received a shitty pizza, also reach out to us and maybe let us know what pizza you would like. So yeah, I think those are pretty much it. We're gonna get started right away. From this banner, I think we have two speakers today. We're gonna be talking about scaling in AI and why this is a big challenge today in the generative vision community. And so we're going to kick it off with Christoph. So Christoph is the head of AI at Signatrix. And so Signatrix is doing something really cool if you looked into it. They're actually monitoring in-store processes and trying to detect and prevent shoplifting, right? And so Christoph is a mathematician, is an enthusiast for generative vision. And so he's going to really take it away by talking about how he's using generative vision to augment images. I think that's going to be really cool. So, Christoph, the floor is yours.
Thank you. So first of all, thank you very much for inviting me, and I will share my screen, and then we can get started. I think you should be able to see my screen now, right? Yes, you do. All right. So yeah, as I said, thank you very much for inviting me to this, and I really look forward to my talk. I will be talking about more or less deploying at large scale of computer vision systems and the kind of data that you bring in and the way that you have to handle this data to not get overwhelmed by it, including some generative parts. And okay, now maybe you can see me in the right frame. And okay, let's get started. So we are Signatrix. You stopped my webcam, I think. Okay, it doesn't really matter because now it's back. Okay. So now you can see me, but first or most of all, you can see my slides, I hope. And so we are Signatrix, and Signatrix is a company that is really a deep learning and computer vision first company for physical retail stores, so for grocery stores, for supermarkets. And we think that there's like a huge potential with deep learning to do stuff inside of retail stores, to make processes better, to give the retailers more insight. And even though Jeff Bezos and a few other people are doing their best to more or less bring everything online, it's still the case that like 90% of the retail that is happening in Germany is happening offline. And even that, if that might go down a little bit over time, it's super interesting and super valuable business and something that everybody's being in touch with every day. And so we want to go with the retailers together into a future where there is a lot of stuff they do better with AI, where they understand everything better, where the customer experience gets better through deep learning. And so we begin with rather small systems, and in the end, we want to build something that's really big, very holistic systems that will touch all the points during a customer's journey and the logistics and everything that is involved in the retail store operation. And so we started our go-to-market with shoplifting. And the reason for that is that every retailer in the world, every person who's working in retail understands shoplifting is a problem. So you can go to them and they will understand what your problem is, or the problem is you're solving, and it is a big problem for them. So it means that there's around 1% of revenue being lost to shoplifting and to similar problems. That doesn't sound like so much, but if you look at the margins of the retailer are 1 to 3% of revenue, it's a lot. So in the worst case, it could be like the stuff they're taking home, the stuff they're actually earning is half due to shoplifting. And so all of them are really motivated to stop it. And that results in it being a $100 billion problem roughly worldwide. So it's worthwhile to tackle it. And this is what we started with. Important there to understand is most of the shoplifting is not happening by somebody taking something from the floor and putting it into their jacket. This is just a small part of it. The most that's happening is really people stealing with certain tricks, with certain kinds of behaviors that they can repeat, especially professional thieves who steal around half of the stuff that goes out of the store. They steal with these kinds of tricks, and so we try to tackle them. And that means we are not just doing like a model that just supervises every person in the store and tries to understand all their behavior. That is not going to be something with a good ROI for now, at least. And so we want to focus really on those tricks. And today I will talk about one of our products, which is called, sorry, I have another slide that is about our customers. We have quite a few of those. Europe's largest retailer doesn't want to be mentioned, but you know all of them. I think all of you have shopped at them already. You might know the others as well. And so we have a few others that are not there. We are also starting to sell in the US, so that is a lot of fun. And it is a bit harder with Corona, but generally it's great. And so I want to talk today about CartWatch Checkout. And CartWatch Checkout is a system that is for the standard checkout. So if you have a checkout and you have a conveyor belt, and so goods are put on that conveyor belt, and then the person is moving through the system, basically the cashier does the whole accounting thing, and then afterwards you pay. And the problem there is that people leave stuff in the shopping cart, and if they do that, they, if the cashier doesn't see it, they don't have to pay for it, and they steal it. The nice thing about it is that if you are being discovered while you're trying this, you can just say, oh, sorry, I didn't see this article, and so you just put it on the conveyor belt and you pay for it, and everything is fine. A lot of stores have mirrors or similar kinds of solutions for this. The problem there is that these mirrors don't work because the cashiers don't like looking in them, and the customers don't like them because they feel like they're being implicated as if they were suspects, basically. And so this is a process that doesn't work well, and it takes quite a lot of time. And we do that with a computer vision system, so basically tiny camera, it looks into the shopping cart, it analyzes the content of the shopping cart, and then if there's something of interest to the cashier in the shopping cart, it will be displayed on the checkout computer. That shapes around 10 seconds of each checkout process, and that is a lot if you have a lot of checkouts and a lot of customers. So that is the product, and we will be talking only about this product today, and we will be talking about this product in the context of really deploying it at scale. And so the product uses two models internally. So really, in terms of deep learning models, it has a soft real-time detection model. So it's looking for shopping carts that are driving past. And if it sees one and the cart is in the middle, so you can see the whole cart, then you will decide on the contents of the cart with a classifier that's just running there and deciding basically, do we want to show this or do we not? And sounds, I think, simple enough. It's like a standard setup that you would see a lot of the time in computer vision scenarios. And yeah, this is how it's working. This is what the classifier might see. So this is an older image that we have taken a while back. So this is one of the founders of the company. And because the Mühr images we can't show you actually, and but here you would say, okay, of course you want to see this bottle of vodka or whatever it is, and so the classifier sees this kind of image. You see the green rectangle around it. This is standard computer vision language for it being the result of a bounding box, and so this is really what the training data might look like, what the inference data looks like as well. And here you also see, because the bottle, it is semi-transparent, right? And that is something that's really hard to understand for a computer vision model, for standard deep learning model, like, I don't know, whatever you would want to use, ResNet or something like that. And so you have to think about how to make your model robust under these kinds of distortions. For a bottle like this, it would be reasonably easy because the bottle is big, but if you have like a small bottle that you get at the checkout of a supermarket, it gets really tricky to see them because they almost look like they're not there. And so these are the kinds of edge cases we will be talking about later. Okay, so how do we deploy those systems in general? We deploy them with NVIDIA Jetson devices, with the Nano or the NX. So a Nano if we have one device per checkout that we are supervising, and an NX if we do the centralized per store. And we connect our systems to the checkout computer, but we can't directly access them. So we have an incoming connection to the camera, and we have an outgoing connection to the checkout computer, but that is it. So whatever kind of communication we do with our systems will be through the checkout computer. And that means that we can't transfer a lot, because the checkout computers, they are in a super restrictive kind of subnetwork where you can't just put a lot of data through, and so you have to restrict what you get from them, which will become later important a little later. So now the problem that we have is that there is basically a lot of change involved into a retail operations. You introduce new products, you introduce changes to the design of your store. You might introduce, for example, new shopping carts in our scenario. And the retailers, they are thinking in decades. They're not thinking for their products in like 1 year, 2 year cycles. So you have to build a product right now that is compatible with the retail surrounding in 8 years. And that is something that's tough, because this data generating process is changing continuously, and you have to think about how can you keep your system basically up to speed so that it will work all the time. And that's the expectation, and the right expectation from our customers, that even just because they introduce new products, our system doesn't stop working. And so the solution for that is quite obvious. I think we collect data periodically from all the machines that we are deploying. And so you get a few images from all of the machines, and then you can, I mean, they should cover on average all the new stuff that's being introduced. And if you see enough data there, it should be fine. And so this leads us to two questions that I will talk about a little bit more or less from now. So how to solve them. And the first question is about what do we want to transfer. And so let's assume we can per checkout only transfer like 10 images per week. That is because of this connection through the checkout PC. We can't just, you know, get all the data that we want. We can just, let's say, 10 images. And so really the question is, which images do you want to get? And if you just say you get some random images, that might be fine. The problem there is that, you know, if you have like 6 stores and you get a few more images, then you might encounter all the edge cases. But if you have hundreds of stores, like this many stores, for example, then you would at some point you would see a problem there that you don't see all the edge cases with high enough probability, because the edge cases are not in all of the stores. They might only be in 1 or 2 of the stores. And so you have a problem. And if you are at this level, where you have really a lot of stores, then you will encounter real difficulties there. So you might need something smarter than just saying, okay, we will take some random images. We will actually go bigger than that. We will go to tens of thousands of checkouts with one single customer in the next few years. And so we really have to think about those problems, because we will deploying tens of thousands of machines. And so that stuff that I talked about, if you take 10 images per week and you have this kind of size, you will end up with 500,000 images at least per month. And so that is really a lot. And so the question then is, after you've selected the right images, what do you do with those? Because you can't just label through 500,000 images per month. That is a big operation, and we are not in the business of doing annotations like at that scale. And so how would you tackle that? How can you do something useful with that data? So again, the two questions are how to select the images and how do you make use of them once you have them in on your server. So the first question, how to select the images. The idea there is you use your current production model, the model that you're running, that you're using to classify the stuff that's driving through the checkout, to find interesting candidates. And what does it mean for a neural net to be an interesting candidate image? That means during training, this image would tell something useful to the neural net. So it would be informative during training. This is actually an underappreciated problem. There are images that are super confusing in ImageNet, for example. There are images that are very confusing to a neural network, and the generalization performance gets worse because of them. But there are also images that are so boring to a network, because the network is it's super sure what the image is showing, that they are also bad for generalization performance. And so you want to find images that are very intriguing, so where the network can learn a lot from. And what would this kind of image be? It would be an image where the network is very uncertain. And the general literature on this kind of topic is called active learning. Active learning is an old branch of machine learning, and there the general idea is that you have a pool of data, and you can train a model, and you can train it quite quickly, and you have a limited budget for what you can, how much you can annotate. And so a classical loop would be, you have your pool of data, you select with some smart strategy, you select one data point, you annotate this data point, you train a model, then you use that model to select the next data point, and you iterate over this process. And so that, of course, is not possible with a big ConvNet, because each training takes, let's say, a day, and so to do that would be not worthwhile. So we need something else, that we're still benefiting from this kind of literature for this. And how does it work in practice? It works by, first, we keep a few hundred images at random. So we don't look at all of them, but we look at most of them. And so per day, we produce per checkout around 700 images, and we might keep half of them. And but that means in these few hundred images, edge cases are with a high probability they're still in there. And then we take our neural net, the one that we have, the ConvNet that we use for classification, and we run it per image 100 times, let's say, and we leave dropout enabled. And that is the very smart trick, because if you leave dropout enabled, you're essentially self-ensembling the model. That means that you're selecting sub-models of the model every time you run through it. And then you ensemble the predictions of all of them, and you get a probability distribution about what these sub-models think of your general model. That's really very cool. Actually, in the so you construct a Bayesian neural net. If you know this kind of literature, you construct a Bayesian neural net out of a normal one. What you would have to do for that is you put dropout after each layer. Then it's actually a Bayesian neural network. We're doing it only after the last layer for convenience sake, so it's asymptotically, it's not super correct, but it's good enough. And so that way you get a probability distribution about the prediction of the submodels for each model, and then we compute the mean and standard deviation of those two, and we select the ones where either the mean is close to 0.5 or the standard deviation is very high. So there's a lot of variation between what the different submodels have said about these images. And yeah, so I have to just to say that. So after that, we have selected the images that are most informative to the current production model, and these are the ones that we transfer. And so with a higher likelihood, those are the ones that are the interesting edge cases for us. Now, question 2: what do we do with all the data that we have collected? And here the problem really is, with 500,000 images, we as a small startup, we are not capable of doing anything like annotating all of them or in one go every month. And so what do we do with it? The solution is we do another round of ensemble-based variation inference. So we do an ensemble of different models, and so we look at the distribution over these images again to select the ones that are interesting. But now it's really different models, so it might be a ResNet and an efficient net and some esoteric nets. This is a name that nobody has used so far, I think. Esoteric net. We should write a paper on that. Anyways, so you ensemble over all of those, and then you select the most interesting images. The other ones, where the models or this ensemble of models is quite certain that these are, for example, only full cards, or this is very certainly a full card or very certainly an empty card, there we say we use them in semi-supervised fashion. So maybe if you know this kind of literature, we don't have time for it now, but something like SimCLR, which is actually using a very big secondary data set added to ImageNet to make more or less the best ImageNet models that the world has seen so far, I think, or at least some of the best ones. And we are using something like that because then the bulk of the images we don't have to annotate because they are basically quite clearly of one class or the other class. And for the rest, now we have a leftover of the most informative images. We have filtered twice and said, give me the most informative stuff with different methods. And these images, we label them by hand. So we want to make sure that we know what they are. And we say, okay, those are the edge cases. Maybe some of them are just broken images. There are artifacts in them, and then we filter them out because we're looking at them by hand. That's not so hard to do. And the rest, we say, okay, these are really the weird edge cases. And edge cases are edge cases by nature. They're in a way where they're on towards the edge of the data manifold that we are looking at. So you have the data that we want to learn, and an edge case usually is somewhere to the some edge of that. I mean, that's where the name comes from. And the problem is that there's not a lot of data around it. So we only have like one example. And so if you train now and you take this same edge case example and you train a lot with that, you will overfit on it. So if you, for example, overweight it by a lot, you will also overfit on that. And that is not so good. And so we want to basically take this edge of the data manifold and produce new samples that are close to it. So let's say we produce a ball or a sphere, and we look at the stuff that is in that sphere, so close to the edge case, and we produce new stuff that is in there. And then we can use that to train again. And we basically covered the edge case and made it to a non-edge case. And that means we generate images that are similar to the edge cases. And that is now actually where the generative learning comes in. And I had to tell you all of that so you can understand why we're doing this. And so what we're doing is we're using StyleGAN. So StyleGAN 2 now, because it's new and fancy. And we're producing images with that. And StyleGAN is really cool because it does these disentangled style representations. So you can steer a lot about the information, and it does that in an unsupervised way. So basically, you just dump all your images in there, and it will learn to control different kinds of styles. So stuff like for a person, stuff like age or gender, you can just control quite easily. And these, I'm pretty sure if you are in a meetup about generative AI, you've seen the website, this person does not exist. And StyleGAN version 1 is what's running in there. So this is like one of the state-of-the-art models for doing this kind of stuff. And so we train a StyleGAN, we can produce images now. We don't do it with the full resolution that they are doing it with because we don't need it. And then after we have trained that, we do a reverse search. So we take our edge case image, we put it into the StyleGAN the wrong way around, and we look for a vector that will produce that image again. And then we basically, so we find an input to the StyleGAN, the noise vector, that will produce the image that we are looking for. And then we can take that noise vector and we, wiggle a little bit with it, and then we can generate images that are similar. And these images basically produce the sphere around the edge case. And so in the end, we cover basically this edge case with additional images. This is like super, super, super strong data augmentation we're doing there. And so that is what we're doing. It's quite a lot we're doing, but it's also quite intriguing and a lot of fun. And so how well does it work? I can tell you right now that what we've seen so far is very good. I won't tell you like 3 MAP points better for something, or because that is completely nonsensical without you knowing what data I'm talking about. But it looks good so far. And of course, we will only learn how good it is once we see the data generating process really shift. And so we can learn whether basically the failure cases that we are producing are going down or they're going up over time. But so far, we are quite confident that this will work well. All right. That is from my side, and thank you very much for listening to me, and I really look forward to answering your questions. And so here we are. So what? Okay. So we have one question that says, can you elaborate on the different shoplifting strategies? And the the problem is there. I mean, I can't tell you that all of the strategies, because then you can just go out and steal with them. But I will tell you one that we have actually built another product for, and that everybody's always finding quite surprising. But I think it's very intriguing. It's through the entrance of a store. So if a store has an open entrance, it is basically there's no gate, right? So you walk in, and in the modern store that is happening quite often. So the reason for that is marketing, because the marketing guys will tell you that if you walk into an open store, you will stay longer. If you stay longer in a store, you will make more impulse buys, and if you make more impulse buys, the margin of the retailer goes up, because the retailer actually earns money on you buying this fancy chocolate and not so much on buying, I don't know, milk or something like that. And so they remove the gates at the entrance, and the problem is now you can drive out through the entrance of a store, and people are doing that quite a lot. They're doing that with full shopping carts, especially professional thieves. And the highest value that we have ever seen that somebody has stolen like this was 4,000 euros worth of goods in one shopping cart. So that's crazy. And that was a store where they had like Dyson vacuums and this kind of stuff. And so these strategies are really being used by professional thieves a lot. So they are taking the shopping cart, they're putting like liquor in there and coffee and the other very expensive stuff, and they just drive out. It takes them like 2 seconds, and then they're out of the store. And if nobody notices it, then they look like a normal customer afterwards, and it's really hard to find them. And so this is really one of the biggest problems that the industry is facing at this point. And yeah, that's why we have a product for it. Okay. For a teacher network with active, yeah, the question is, what kind of loss function do you use for a teacher network in active learning and for style gun? For the teacher network, we don't have an active learning teacher network, so we are not using that. I mean, the active learning part is really the data selection part. Maybe you mean the semi-supervised stuff, and there something very close to SimCLR is what we are deploying right now. So for the data points that are not labeled, you will run through the image twice, or through the network twice, once with a non-augmented data point, and once with a very heavily augmented data point. And then you will look at the scores you get for the non-augmented data point, and you will basically say, okay, this is the network is very certain of this, and then you use that as the ground truth and use that to train with the second data point that you've produced with a lot of data augmentation, and that is the one that is actually giving you a gradient there. But then the loss is just, you know, I think percent rupee in the or something like that, you know, standard losses. And for the style gun, if I'm not mistaken, we're using Wasserstein GP for that, I think. But I don't know, to be honest, I would have to look that up. Okay. Yes, then the one question is, you presented the approach for classification. Does it work for detection too? And yes, it does work for detection, but it's much harder for detection because the active learning part is much harder. So if you have a classification network, it will tell you, okay, here's more or less its output is a probability distribution over classes. That is a very simple probability distribution. So all this kind of reasoning is quite simple. But if you do something where you have the output of a detection network. It will tell you things like, okay, this is a point and there I think there's nothing, and this is another point there I think there's nothing. And the problem is that some of those points there's actually something there. Some of those points there's nothing, but you don't know which is which. And so you don't know where you have a true positive, where you have a false positive, where you have a true negative and a false negative, and especially false negatives are really, really hard. So if the network is not seeing something in any kind of data or in a data point at all, but there's something really there, it's super hard to figure that out. And so you have to think about a much more complex probability distribution, basically, that you have to generate for those kinds of networks. So it works, but it is much more complicated, and we're not doing it because the detection is quite easy for us, because you see a super big shopping cart where we go, right? There is a very big shopping cart or not, and so the detection just works for us, and so we don't do that because it would be a lot of additional work. Yeah, so yes, then there's one more question. Is there a probability of bias creeping in with high class imbalance? Yes, you have to sample for that. You have to make sure that your classes are reasonably balanced, or maybe you wait a little bit. We have different approaches there, but that is definitely a problem that you will encounter. So for example, in Germany, like 70 to 80% of the shopping carts, I think, are completely empty that go through the checkout. That's completely different in the UK, for example, but still, you have to think about those kinds of probability distributions. All right, then I would say thank you very much, and I hand over to Sebastian, or to hand over to you. I will definitely check the screen share. Thank you.
Brilliant. Thank you so much for that. That was really exciting. And I think I'm gonna actually try to tackle the first question there was, which was, what is the goal of the meetup? And so before introducing Sebastian, I think maybe a quick preview of what we're trying to do here is, you saw what Christoph spoke about, and you saw even for like a different application, he still is immersed in the field of GANs. He's talking about active learning. And so really the goal of this meetup is to get people from different streams and different paths who are probably working on the same problems and discuss these pain points and see if there are mutual overlaps that we can talk about, and then maybe figure out solutions for that. So Christoph spoke about Signatrix and the work that he's doing with GANs in that space. What Sebastian now is going to do is, I've given you an idea of what Brighter AI does, but he's the technical lead at Brighter AI. So he's obviously going to start off with a technical introduction to the ecosystem inside the development of Brighter AI, and then he's going to talk about scaling AI from edge to cloud. Sebastian, the floor is yours.
Thank you, Joy, and thank you everyone for joining this meetup. So I'll also jump into sharing my screen and then go right into the presentation. And let's start this. So yeah, as Joy already mentioned, I'm the tech lead here at Brighter AI, and what that means is that I don't actually work directly on the machine learning models here, but I make sure that we actually make products out of it that customers can use, that it's scalable, that it's maintainable, and all that. And I'll be talking about exactly the scaling the generative AI aspect. So it will be more architecture focused and software engineering focused rather than deep learning focused. But before I jump into that topic, I'd like to give you a brief overview over what we as Brighter AI are doing on a product basis. So we're a privacy company. We're anonymizing all kinds of visual data, so images, video, live streams. And we're doing that with a technology that we call deep natural anonymization, which basically means we put artificial faces on real faces, artificial license plates on real license plates. And you might be wondering, why don't we just pixelate this? This is because then your data wouldn't be usable anymore for any machine learning or data analytics applications. So what we really want to be is a real transparent layer, basically, that you don't have to worry about the privacy in your data, but it's just there and you can train your models on it. And since we're coming from automotive background, the self-driving cars are a big application actually, because you don't want your model for self-driving to only recognize people if they're pixelated, because in real world they're not going to be pixelated. And that's basically what we are doing. And so now, what's the challenge that we are facing? Basically, since we are in this privacy space, we want to be really close to the camera with our application. So that means if we could anonymize directly on camera, that would be ideal. Then no privacy breaking data would ever leave the camera. So that's where we want to be on the edge. But also we have customers who already have collected a lot of data and want to maybe publish the data or share this data set with other divisions of their company, other companies, but they can't because there's personally identifiable information in there. And so now we want to basically train our anonymization models once and deploy them either in the cloud, where you can process these big data sets, or on edge, very close to the camera, so you can directly get the anonymized data feed. And actually, it's more than just training once. It's also building our software mostly once, some special stuff that you still need to do for every environment, but we will get into that later. And at first, this might sound quite easy, but if you then start looking at all the different platforms that you might want to deploy your solution to, they are actually quite different. Like, so for us, we're supporting basically cloud, we're supporting small data centers, we're supporting your run-of-the-mill development machine, but also we're running on NVIDIA Jetson, which is already quite a bit different because it's using ARM-based processors, which yeah, it's just very different from your x86. Then if you go even smaller, you will end up at some point really on embedded hardware and integrated circuits. That's not what we're going to talk about today because it's a whole new field basically, and there you probably just want to hire some specialists there. You will not get an easy solution. And so now let's look at the two things specifically. What does edge mean? What does cloud mean? What are the different requirements we face there? On the edge, what we really care about is getting the most performance out of each single device, because we only have one device on the camera, and that one needs to be able to real-time anonymize everything. And in the cloud, we care about scalability. We don't care what one of our nodes in our cluster can do. We care about that we can spawn a lot of these and that we can really balance the load over all the different nodes in our cluster. For the edge, this basically means low resource usage is key, because if you use fewer resources, you can go onto even smaller devices and use less power, be cheaper. So that's really where you want to be. Cloud, cost efficiency is still key, but it's not, again, about how cheap is each individual device, but how much does processing cost. And for us specifically, on the edge, we usually deal with a few live streams, like 1 to maybe 16 camera feeds on one of these NVIDIA Jetson devices, which basically means we care about latency. So if something happens on your camera feed, you want to see it very soon on your anonymized data feed. On the cloud, it's very different. We have just a very high volume of videos that's being put through by multiple customers into the same cloud. And there we don't really care what the time between frame in and frame out is. We care about, hey, I put this big video in, how long is it going to take to process the entire thing? So the throughput or bandwidth is basically what we're looking to optimize here. And since this might all sound very abstract, and I also don't want to just throw like our entire software diagram at you, I've come up with a simpler way of demonstrating it. A simple showcase which will basically have the same challenges that we have been facing, and where I will highlight the learnings that we've had along the way, but on a different imaginary product. So imagine yourself being an artist, and you want to run an art exhibit where you want to show off the latest neural style transfer, so people can walk in front of a camera and you will just apply this style transfer and show it on the display, and that's basically your art exhibit. But since you want to have it a bit more interactive and not just apply the same style transfer all the time, you decide that if there's more people walking into the frame, you want to change the way that you're stylizing this. And with that idea in mind, you basically start prototyping. So this is maybe Python-like looking code, but it's just pseudocode. So I know this will not run. So all you're doing is basically you're getting an input stream, and you're then splitting that one into the individual frames. For each of these frames, you want to detect people. You can use out-of-the-box person detectors, or you train your own one. For this case, it doesn't really matter. By that, you can get the amount of people in your frame, and then, of course, you want to stylize the image actually, but have some factor in which style to apply based on the people count. And in the end, you still need to serve it back to the user. So just show it on your screen. And that way, you basically build your first pipeline, which consists of the splitting part, just the frame into individual, the stream into individual frames, and then the counting part, which just means count people, stylizing, and in the end, serving it back to the user. And with that, you have success, because you now have your art exhibit and you have your prototype running. It's running on your nice 2080 Ti, on your dev machine, and it's working. And now art galleries are starting to contact you. They want to have the same thing, but smaller. They want to set up multiple booths of these everywhere. They want to maybe even take it mobile and walk around. So this sounds very much like an edge use case. So you think, okay, let's go to the edge with this. And you realize, okay, this edge device, so the NVIDIA Jetson in this case, has a lot less power than my 2080 Ti that I'm running in my machine. So how do we make this now happen in real time? So there's a few frameworks that can help you there, which is, for example, Deepstream. You can optimize your models with something like TensorRT, but in the end, you're basically just throwing the same pipeline into just some framework which is optimized for this platform. And it's not entirely the same pipeline, because you still, actually the framework in this case, it will take care of encoding, decoding, a lot of the frame splitting. But just to keep it simple, imagine you're basically doing the same thing, just in a more efficient way. So we've optimized it to run there. Each of these could be their own topic, so I will not go into details on these tools. And yeah, you're now on the edge. You have more success. So now not only art galleries are contacting you, but even the people visiting your galleries, your exhibits. They want to stylize their own videos. They have some on their phone. They just took some nice vacation videos. They want to stylize them, but they don't want to buy like this clunky device from you, or even put like a big machine in their home. They just want it on the website, basically, and just drag and drop their stuff in and get that stylized. And so, yeah, you say, sure, let's go online. So then you start taking your entire application that we've had before. You put the thing in the Docker and maybe give it something like an HTTP handler, so you can build a REST API, can put a fancy front end in front of it with drag and drop and everything. And that's great. This thing you can then host on a cloud provider of your choice. Or it could still be just running on your dev machine in your bedroom with a static IP, and that would still be technically online. But now, what happens if you have even more success? You might be asking, like, maybe not 2 people want to use it, maybe 100, maybe 1,000. In the beginning, you can still just scale it vertically. So that means buying a bigger machine, renting bigger virtual machines in the cloud. And actually, that's a good case to be made, depending on how much you need to scale it, because scaling vertically actually avoids a lot of the issues that we will be talking about next. But at some point, it's prohibitively expensive to just scale vertically, and you will run into limits there. But you can be very efficient on single machines, because it's just one machine. You can share memory and all the good stuff, basically. But like I said, if you have too much success for your one machine setup, you probably need to think about scaling horizontally. What does it mean? Basically, you just take your application, you start more than one of them. They might be running on their own machine, put something like load balance in front of it, and just spawn as many as you need. And yeah, you think you might now be as good as it gets, right? No, not really. So you can probably identify already some bottlenecks in your architecture. Like the stylizing is probably going to take a bit more efforts than your counting, and definitely more than splitting and serving a video. So wouldn't it be nice if you could just spawn multiple of the stylizing ones? Because right now you probably are load balancing starting this entire thing just because your stylizing is bottlenecking you. Also, right now, different jobs can be interfering with each other. Let's imagine you just pump in a big video into the first one. If anything else gets put in there, unless you have a really smart way of queuing stuff, then it will probably be blocked for a long time. And you basically don't want one user putting large volumes into your system to be blocking other people's processing. So maybe you then start thinking about microservices. So actually just taking the individual services that we talked about before, so splitting, counting, stylizing, surfing, just put them in their own Dockers and use some container orchestration, for example, Kubernetes, to manage that. And yeah, now everything is nicely decoupled, looks good. But remember, with our code that we have here, the frame that gets read in the splitter, it somehow needs to be passed on to the counting and also to the stylizing. And you also need to somehow pass your count actually over to the stylizing as well, so it can stylize. And of course, in the end, you also need to forward the stylizing to the stylized image. One solution to that is use like an event-driven architecture. So that means you have some form of message bus to communicate between your services. In this case, for example, you can use Kafka. Other options are available. And basically what you do is the splitter will just notify into the Kafka that, hey, yeah, there's a new frame available. Then the counting will pick that one up and do its counting on there, say, yep, I've got now a count for this frame. Stylizing will pick that up, say, okay, now I know the count, now I have the frame, everything's there. I'll just stylize it, and serving will, well, then serve it and take the result. But since there's something like a frame, which you will have in like all computer vision applications, probably some visuals, you probably don't want to base 64 encode your 4K, 8K massive images into the message, because it will just blow up your messages. And basically, that's just not good design. So you might add something like a cloud file storage, which will also make it easier to share the files between the different services. So you don't have to send this big message to every single service, but actually you can just store it in the storage and then have a path to where to find it in your message, and then just all the services can access it if they need it. And here I'd like to mention something that we had to learn the hard way. You might have not noticed much of a change between these slides, but there's actually one little word here, which means really think about the way that you're designing your services, because counting is nice and good because you need that in your stylizing. But what if you now want to change the way that you stylize? Maybe it's not good enough anymore to just change it based on the number of people, because usually maybe there's only one person working front, so you will not see all the different styles. So maybe you want to base it off of the position of the person in the frame. Now, what do you need to do? You need to make this service somehow a position-giving service, and then change the message that you're sending over here. Know what message you need in here, but actually you just want to change the stylizing. So yeah, just give out the entire bounding boxes in here and the probabilities even, and the entire result. It's quite cheap to just add a couple bytes to your message. Still don't add your massive megabytes big image there, but if you have some metadata, just add it in there. That's cheap. And don't basically pre-process the output of this just because you know there will be a service later. Then you're not really decoupling stuff. So we had to learn that the hard way, and especially for images. For example, if you deal with cropping parts of them for a secondary classifier, for example, don't already crop them exactly the way that it needs to be cropped, because you know the model in the next service but rather just hand the entire frame over and tell it, yeah, that's my box, and you now do with it whatever you want. And now what we're adding is actually interfaces of each of these services, because you might be thinking, hey, this is a lot of custom stuff. I thought we would be talking about how to unify edge and cloud and not reinvent it every time. And that's where these little things here come in. So these are basically just abstracting away what's going through the Kafka. It's basically just a way of communicating between services and a way to get your binary data basically in the cloud file storage. But what does this actually look like in code? I've just exemplified it here. So you can use something like dependency injection. It's a good software architecture principle to use. For example, what you actually want in your detecting services, you want a way to be notified about a new frame being available, and also you want to have something where you can get your frame from. And basically what you just want to do is subscribe to this frame notifier and say, okay, yeah, if there's a new frame, please tell me. I don't really care that there's a Kafka behind it. I don't really care that I'm running in a Docker that I shouldn't know in my module, the detecting module. And then when you receive your frame, you just ask the frame source, yeah, you apparently know how to get a frame, so please hand that over to me. And then I can still just do the same processing of the frame and detecting my people in there, and then tell back to this frame notifier that, yeah, I want to publish now the detections that are available for this frame. And yeah, this now, like I said, we want to come back to how to apply this also for the edge and not build two completely separate products. What you basically do is you see these little black lines in here, basically almost plug your services that you've built together. So they don't need to have a Kafka, like I said. They can literally just be very dumb implementations of the same interface. So your frame notifier here could just be something that's calling the function in the next service and just basically is directly calling it. Or maybe you have some in-memory queue in there, just some, a queue in whatever language you're using. And then basically you still have your services. This part in here is completely agnostic of what's happening on the outside world. But of course, this is not a silver bullet. You're still adding more abstractions. You're still, not using maybe keeping stuff in GPU memory all the time, unless you define your interfaces to always give you like a GPU memory pointer instead of the actual frame. And so you can get around that, but usually you're sacrificing some performance there, because yeah, that's also one of the key takeaways here. So to summarize, use modularization. If it fits, then just treat it as business logic and basically use any best practices that you already know from other software engineering. So it's AI products are still software products, so treat them as such and apply these best practices. And also, there's no free lunch, so there's trade-off decisions that you need to make. If you want to have the best solution for edge, the best for cloud, then build two products, optimize them individually. But if you're a small team who wants to cater to multiple different platforms, then please try to find this middle ground, abstract away these different platforms, and you will be quite happy that you can deploy it there. And with that, I'd like to say thank you to everyone. I would love for you to get in touch with me. I know this was a very high-level, broad overview, but if you want to go into more depth, I'd be very happy to. And I'd also like to just meet up for a coffee. I'm up for that. So yeah, with that, okay, I'll take questions first. So one question is, how do you handle the high computation cost of video processing? Do you simply queue them in case of overflow? Does a load balancer handle this? This is a threefold question, basically. Yeah, so the high computation cost of video processing, well, you can run GPU instances in the cloud there, but depending on your load, it might actually be okay to just use some CPU instances if you really don't care about how long like an individual frame processing takes, as long as you can scale horizontally. And yeah, for the vertical scaling example, yes, you just have a queue and stuff gets backed up. But for the horizontal one, yes, have a load balancer and auto scale basically your different instances, so that in case your queue gets too full, you spawn more workers to get more quickly to the queue. Okay, then what cloud provider are you using, and do you use ML orchestration platform like SageMaker in case of AWS for model training and deployment? We're currently using Microsoft Azure as our cloud provider. And no, we're not using any of their machine learning orchestration, but we're currently in the midst of implementing MLflow for our internal management of different machine learning models and releases, and basically having them in different flavors like the TensorRT stuff that I talked about before. Yeah, but we're not using anything cloud specific there, just having our own MLflow setup. On the edge, how do you handle multiple GPU-based Docker containers? You only have the embedded one available, right? Yes, that's correct. But we just don't have multiple GPU-based Dockers running on our edge. It's basically just one Docker running on the edge device, so the NVIDIA Jetson. But you still have these services in there. Maybe I didn't say that specifically enough. These services here, they are not encapsulated in individual Dockers anymore. It's basically, you can think of this as one Docker, and so they will just be using one GPU and not, so there's no competing services, at least in our case. Okay, then that's it. And I'll hand it back to Joy. Thank you again very much.
Okay, excellent. Thank you so much for that. You took a couple of questions. That was great too. So I hope you guys liked the talks. What we're going to do now is actually open it up for a broader discussion.